Hello everybody, and welcome to this lecture on computer architecture. Today I want to talk to you about the sum of products and the product of sums, or in another way to put it, how to implement any logic from any number of variables based on the three basic gates that we have found in the previous lecture. Let me remind you where we are now. We have been starting with Huntington postulates to implement Boolean algebra. We found out that we can work with this. We have three basic gates, or three basic operations, as you should call it. We don't have gates yet. This will come later. But we have these three operations. That is, we have not, the not operation, the or operation, and the and operation. The not is just the complement or the inverse of the variable a. Or we'll take a or b, and you can see here what it will result in. And we also have the operation a and b. And to remind you, to put it in a truth table that we have done then based on these Huntington postulates, we found out that the truth table of these three operations are like this. So for the AND, we have that the output is 1 if both inputs are AND, or I should say operands, because we don't talk about inputs yet, we don't have gates yet. So if both operands are 1, true, then the output is 1, true. And for the OR gate, for the OR operation, we have that the output is 1 if either or both operands are 1. If not, then the output is 0. Then the result is 0. And the NOT operation is just the invert. If the operand, the single operand, is 0, the result is 1. And if the single operand is 1, then the result is 0. So how to use that now? Imagine that we want to have any kind of logic function from any amount of variables. I take here an example. Imagine that we have a function f that has three variables as input, a, b, c, has three operands. How to implement this table, this truth table, how to implement this on basis of these three operations, AND, OR, and NOT. Well, this can be done by the technique of sum of products and product of sums. And to remind you, we're not talking about sums and products, but we're talking about AND and OR operation. But just because this symbol here, this dot, reminds us of a product, we call this a product. And because this symbol reminds us of a summation, actually we call this a sum. But we should always keep in mind that these are AND and OR operations. So let me start first with how to implement by the sum of products and then by the product of sums. So the sum of products, I would first like to point out to you that let's imagine we have this function m0, and you will find out in a moment why I call this m0. But imagine we have this m0 function, and that is actually this function that is not a and not b and not c. Well, easy calculation will show you that the truth table of this is given below here. It is 1 and only 1 for only this combination, namely a equals 0, b equals 0, and c equals 0. As you can see, this will be not 0, which means 1, and not 0, which means 1, and not 0, which also means 1. So 1 and 1 and 1. Of course, this is 1. And we can take any other entry in the truth table, for instance 1, 0, 0. This will be not 1, that's 0, and not 0, that's 1, and not 0, that's 1. So that will be 0 and 1 and 1, and this of course is 0. So you see that this function that I have here, this logic, is represented, or this is written out as this truth table. So now let me put then also, to compare, I will take here another function, m1. This is the same as m0, only that the c is not inverted, but it is direct. And this function will make the second line in the truth table 1 and all the others 0. And I guess that by now you already get the idea that you can have any line here in the truth table will correspond to one of these what we call products. So let me then put this, all these terms, which we call terms, all these functions that would implement a single line of the truth table. So we get this here, and we have here a summary of every line then with what we call a min term. This min term is the line, is the function that would implement that line of the truth table and make that line in the truth table 1 and leave all the others 0. So now that we know this, we can actually use an OR gate or an OR operation to implement any logic table, any truth table. And that I have done here. So imagine that we want this to implement this truth table, this function f. Then what do? We just sum, we just OR all the min terms that have a 1 in front of them. So it would be this one, m0, or m2, or m3, and nothing more. So this function, this logic function, is implemented by the sum of products of the min terms 0, 2, and 3, because in the 0th line, the 2nd line, and the 3rd line, the truth table had a 1, and all the other lines in the truth table are 0. So the final solution to our question then is how to implement this truth table that would be with this sum of products. And then to have an example in a circuit, well, we don't have circuits yet, but I will give you already a peek review. It would be something like this. Imagine we wanted this truth table. This picture I borrowed from myself from later on, but we will get this idea. If you have this truth table, you just copy every line that you have here and make a gate based on that min term. So for instance, if you take here the 3rd line, this is 0, 1, 2, 3, the 3rd line, it corresponds, this line corresponds to this AND gate where A is inverted because it has a 0 here, B comes directly, and C comes directly, and then we get this. This, of course, this is 1, here will be 1, on this line will be 1, for this combination 0, 1, 1 at this gate. And then 5 will implement this here line of the truth table, and number 6 implements this line of the truth table, and number 7 implements this line of the truth table. And then at the end we will sum them to get this entire truth table. So this circuit that you see here on the left implements this truth table that we wanted to implement. Of course, I have to say here beforehand that the circuit can still be simplified, probably. This is not the end solution, but this is a way to, without any doubt, result in a circuit or result in a logic function, that in a boolean algebra function that implements the logic that we want. We can still simplify it, as we will see, with Carnot maps and other ways, or just simply by logic itself. It's still possible to simplify it, but this is a way to for sure get an answer. On top, we can also simplify it by converting AND gates and OR gates to NAND gates and NOR gates, which actually also makes the circuit simpler, because as we will see, AND gates and OR gates have more transistors than NAND gates and NOR gates. That's for later in a moment. So this is how the sum of products works. And in the same way, we can make the products of sums. So how does this work? Well, once again, let me show you this. Let's see, we have this function m0 that is A or B or C. As you can see, this will be 0 for the combination A equals 0, B equals 0, and C equals 0. If not, any other combination of A, B, and C will result in 1. So what it is actually doing, this term is introducing a 0 in the truth table and leaves all the other as 1. And then we can take, for instance, the 2nd line in the truth table. If that is A or B or not C, then this will leave a 0. This will create a 0 in the 2nd line, or in the 1st line, I should say, of the truth table. So M1, which we now call the max term, will introduce a 0 in that line in the truth table and leave all the others 0. And then how to make then a general truth table is then we just show all the max terms, as they're called now, for every in every corresponding line. So we have here, for instance, that 101 will correspond to a max term that is not A or B or not C. And then how to make a general truth table? Well, I'll give here an example. Imagine we have this truth table here with zeros in line 1, 4 and 7, and all the other lines have 1. Then we just copy these the corresponding max terms, M1, M4 and M7, and then use them in a logic AND at the end. So this function that we have here, where the truth table is given here on the left, is actually implemented by M1 and M4 and M7, and that is written out here in Extenso. So this, what you have here, is actually implementing this truth table, and we write this in shorthand as pi 147, meaning that the lines 1, 4 and 7 actually in the truth table have a 0. And to go back to this, I forgot to say this, the same we had for the sum of products, where we say sigma 0 to 3, meaning that in lines 0, 2 and 3 of the truth table there's a 1 and the rest is zeros. And then of course when there is a 0 in the truth table, we have it in the sigma represented, in the pi represented, it's not in the sigma, as you can easily understand. And the product of sums circuits would be something like this. Once again, a peek view to the future, which we're going to do. We all have OR gates here, a layer of OR gates, where every OR gate implements a line, a max term in the truth table, and it introduces a 0 there. So this OR table, this OR gate will implement this 0 in the truth table, because A, B, C 0, 0, 0, this output will be 0. If not, it will be 1. And then we will AND all the 4 OR gates as input. We will AND them and to deliver the output. So this Q, then this AND gate produces these 4 zeros. So that is the way then to summarize is that with a sum of products and with products of sums, the technique, we can implement any logic function of any amount of variables. And the things that have to be said, it can still be simplified, the circuit, or actually we don't have a circuit yet, but the equation or the expression, the boolean expression, can still be simplified, but that is for a later worry, actually, when we are going to talk about Carnot maps, and later about NAND gates and NOR gates, because they are cheaper, they are simpler. So I hope you enjoyed this lecture. See you in the next one.